This video discusses matrix inverses. We begin by defining an important matrix, I. I is a matrix that has entries either 1 or 0. Ones are drawn diagonally down the matrix, and then every other entry in the matrix is 0. So this is a depiction of an n by n matrix. So there are n columns and n rows. This gives the n by n identity matrix. So this is the n by n identity matrix I. For example, if you'd like to see an example of an n, you could do n equals 3, and the 3 by 3 identity matrix is 1, 0, 0, 0, 1, 0, 0, 0, 1. So this is the 3 by 3 identity matrix. It follows that if you have the identity matrix and you do matrix multiplication, A times I will always just give you back A, and if you do the matrix multiplication in the opposite order, I times A, you also get back A. Here, I is the identity matrix of the right size to make the matrix multiplication possible. So this is telling us that the identity matrix acts like multiplying by the number 1. In the world of matrices, the identity matrix is what you can multiply by with to change nothing. So A times I is itself, I times A is itself. Let's see why that's the case with an example. I think after we do an example, you'll see why this is true. Let's do a 2 by 2 matrix. So what if I did 2, 1, 1, 4? Let me multiply that times the 2 by 2 identity matrix. 1, 0, 0, 1. So if I do this matrix multiplication, remember how you do matrix multiplication. You take this first matrix and write it here. That is multiplied by the first column of the second matrix. That'll give you the first column of the multiplication. And the second column is similar. So you start with this matrix, 2, 1, 1, 4. And multiply by the column 0, 1. So if you do the matrix multiplication, watch what happens. I get 1 times this first column plus 0 times this second column. So I'm going to get 1 copy of the first column and nothing else. That means I get the first column, 2, 1. The second column of the matrix will be not the first column, but yes, the second column. So I get 0 copies of the first column and I get 1 copy of the second column. So that means I just write down the second column, 1, 4. So because I have 1s and 0s in this second identity matrix, that's why when you do the matrix multiplication, you get back exactly what you started with. Why don't we do the matrix multiplication in the reverse order, because I times A should also equal A. Let's see what happens there. So what if I did the 2 by 2 identity times 2, 1, 1, 4 again? Well, if you do the matrix multiplication, you'd have the first matrix written first times the column 2, 1. Then you're going to have, again, the identity matrix times the second column. Let's see what happens here. So this time I'm going to get 2 times the first column. The first column is just 1s and 0s. So I'm going to get 2 in the first top entry plus 1 times the second vector. So I'm going to get 2 times 1, 0 plus 1 times 0, 1. So I'm just going to get back the column vector 2, 1. I'm going to get 1 times this first vector and 4 times this second. So I'm going to get 1, 4. So hopefully you could see with this example why it's the case that A times I is A and I times A is A. This is just, again, taking the role of the number 1 in matrix land. The number 1 is also known as the multiplicative identity because whenever you multiply by 1, you just get back what you started with. And that's why I is the identity matrix. All right, so this is a video on inverse matrices. I defined the identity matrix. Now I could define the inverse matrix. So the matrix A has an inverse, and it's denoted A with a -1 superscript. This does not denote 1 over the matrix A. That doesn't make any sense. This, again, denotes the inverse matrix, just like we use the same notation to denote the inverse function. In fact, these are very related concepts. And we define the inverse matrix if these two properties are true. So A times A inverse is equal to I. That's the identity matrix. And A inverse A is also equal to I. Let's see an example. So the inverse to the matrix, how about we do 1, 2, -1, -1, is the matrix -1, -2, 1, 1. I claim that these two matrices are inverses. Why? Well, we'll just check. If I take these two matrices and multiply them in either order, so 1, 2, -1, -1 times -1, -2, 1, 1. If you do this matrix multiplication, you actually write it out. By now I've done a few examples and I don't feel the need to do everything in gory detail, but I think if you do the operation, you'll find the identity matrix. And similarly, if you do them in the reverse order, remember, A times B is not equal to B times A. Matrix multiplication, you can't always switch the order around, but for inverses, you can. If you do the other operation, you will also get the identity matrix. That's why they're inverses. Not every matrix has an inverse. In particular, the matrix 1, 1, 1, 1 has no inverse. Why is that? Well, let's suppose it did. Let's suppose you could find a matrix A, B, C, D that multiplies with 1, 1, 1, 1 to give you the identity. If you actually did this matrix multiplication out, however, if you did the operation, you would get A plus C, B plus D, A plus C, and B plus D. So this would be the result of matrix multiplication. This can never be the identity matrix, however, because if this were the identity matrix, you'd need this top entry to be 1, and you'd need this entry to be 0, but they're both equal to A plus C. So it can't be possible. So some matrices have an inverse, like this one, and some matrices don't. It's similar to the fact that some functions have inverse and some functions don't. If you remember to pass if a real valued function has an inverse, it has to pass the horizontal line test, so not every function has an inverse. Similarly, not every matrix has an inverse. Now, in this class, we're just doing the very basics of introducing matrices and inverses. So we're not going to go into the full detail on how to find it. I think in this class, it'll be enough to only give a formula for finding 2 by 2 inverses. So here is a formula for 2 by 2 inverse matrices. So let's say I have A, B, C, D, and I'd like to take the inverse matrix. The inverse is 1 over A times D minus B times C, the matrix D, negative B, negative C, A. So this is the formula for the inverse of a 2 by 2 matrix, and it only works when AD minus BC is not equal to 0. I'm dividing by AD minus BC, so if that were 0, this wouldn't make sense. Let's check that the inverse to this matrix is indeed what I found over here. So for example, 1, 2, -1, -1 inverse would equal 1 over, now A is 1, D is -1, so I multiply those two, and I multiply these other two and subtract, so I think I would get plus 2 times D, now D is this bottom right corner, so I get -1, negative B, so I take this entry and I just reverse the sign. I take this entry and I reverse the sign, and then I put A on the bottom here. So I indeed get the matrix -1, -2, 1, 1. Now there are formulas on how to find 3 by 3 inverse matrices and so on. There's algorithms or step-by-step procedures to find inverses, but we're not going to necessarily go over that in this course. I think for us, a 2 by 2 inverse is enough. Okay, fantastic.